Welcome, ladies and gentlemen. We are Team Agro-Bot. We have developed an innovative solution to solve one of the major problems faced in agricultural sector. In this video documentary, we are going to share our project experiences, our design methodologies, our component selection, our point of failure, and how we overcome that in a smart way to accomplish this project. The ultimate goal of this video presentation is to provide our viewer a pretty good understanding about the way we carry out the project, and at the end of the presentation, we expect that each viewer can trace our path. So folks, we have segmented this video presentation mainly into 5 segments as introduction, overview, methodology, results, and conclusion. Without wasting any time, let's get started. Starting off with introduction. I would like to start this part with a small video about the agriculture and food security. Let's watch this.
The global food system is under pressure. Over the next 35 years, the growing global population will demand more food than has ever been produced in human history. But food security faces a number of challenges across both production and consumption, which research will be essential to solve. Agriculture is essential, but uses 70% of all fresh water, produces around a third of all greenhouse gas emissions, and can lead to biodiversity loss and soil degradation. With no new land for agriculture, finding new methods to sustainably produce more food on available land will be essential.
So folks, with this video we can understand due to the rapid growth of the population, the demand for the food has been increased. To meet the demand, we have to increase the production. But there are many threats to the food security and agriculture as mentioned in this video. Apart from that, we also need to consider some other threats as well. For example, climatic change, excessive usage of pesticide, growth of plant diseases, lack of human resource. In this project, we are going to target the two main threats, which are excessive usage of the pesticide and growth of plant diseases. Let's look in detail. We all heard about this quote, too much of anything is good for nothing. This is applicable in this scenario as well. Excessive usage of pesticide is harmful for both plants and humans. If we consider the large-scale farming and traditional farming, in both the cases, the farmers use large quantity of pesticide. This is very harmful for humans as well as for the plants. The cultivation land will lose its fertility because of this approach. In addition to that, the humans will be the victims of uncurable diseases in the long run. Apart from that, if we consider the statistics of the leading food producers in the world, China, United States, Brazil, France, and India, we can see that the usage of the pesticide has been increased from 1990 to 2014 and is keep on increasing. So we can see there's a serious issue is lying in the world which yet to be solved. So our team realized the importance of this issue and we proposed an innovative solution to solve this problem. We plan to integrate contemporary cutting-edge technology such as robotics, computer vision, and machine learning in an innovative way to develop our solution, which we call Agro-Bot. So folks, Agro-Bot. Agro-Bot is a robot which can travel over the row crops based on the Bluetooth navigation and detect the disease spots and stress found in the plant leaf. Later, we map our findings in a 2D map, which can be used by a farmer to visualize the infected area of the farm. In addition to that, with the collected result, we predict the growth of diseases. In this project, we target Kampala as our test crop. Apart from that, we limited our scope to find two diseases, namely aphids and the leaf miner. These are the features of our product. I hope that introduction session we have given a brief idea of our project. Okay, ladies and gentlemen, let's dive into the overview of our project. Overview of our project consists of 4 main parts as you can see here. We have the bot control, image processing unit, power supply, and the data visualization unit. The bot control focuses on the chassis development and the navigation part of the robot. If we consider the image processing unit, it focuses on developing the image processing algorithm using CNN to detect the plant diseases. The power supply focuses on fulfilling the power requirement of the attached components. The data visualization unit focuses on representing the data in a graphical format in a web portal. These are our team members. Each of the sub-modules was splitted among the team members as shown in the arrows. I hope by now we have established a problem statement and overview of the project. Let's begin our discussion about the methodology. I would like to start our discussion about methodology with the environmental analysis. It is very important to study about the environment before the implementation. But unfortunately, we failed to follow that approach. We have done the analysis after the failure of first implementation phase. One of the mistakes that we have done in the first implementation phase was we assumed a lot of things instead of practically examining it. This approach backfired us. Later, we realized our fault and we started to investigate in depth. We went to Horticulture Institute and a National Agricultural Park in Gunner River to collect the data about the row crops. As you can see in this picture, we collected the dimensions of the row crops, soil types, and we examined the terrain. When we are questioning the research students who were responsible for the field, we realized that they mainly focus on the yield and growth rate of the plants than following the standards. Since they are given a fixed amount of the land, they are requested to develop 54 rows. So they reduce the gap in between rows in order to achieve that number. From that moment, we understood that we have to focus on a scalable robot rather than a fixed size robot. Next thing that we have analyzed was the soil type and terrain, because the robot has to move in that gap properly without slipping. So we examined about the soil texture and the friction, and we identified is a good and smooth terrain to navigate the robot. Now let's keep these requirements that we are gathered in our mind and let's proceed with our design approach. Okay folks, welcome to the design and methodology part of the bot control unit. Basically, the design approach is split into three main parts as mechanical design, embedded design, and software design. So let's discuss one by one. Mechanical design. It consists of two main parts, which is chassis design and the wheel selection. If we consider chassis design, so far I have designed 6 designs. These are the design requirements of my robot: scalable, lightweight, low cost, stable, and user friendly. So far I have designed 6 designs. So we're going to discuss pros and cons of each design one by one. Design 1. So this is my first design, which was done with lots of assumptions. In this design, we plan to spray the plants as soon as we detect the disease. But when we proposed this solution to the evaluation panel, they suggested us to reduce the scope of the robot since the scope is too large for the final year project. So we removed the spraying mechanism and the solar panel from our design. In the design 2, this is our first implemented design for the first evaluation. The mistake I have done in this design was I rushed on the design phase and constructed the bot with galvanized iron. The resulting robot weight was 32 kilograms. The robot has the ability to adjust the height automatically. This was achieved using 2 linear actuators like this. The main reason behind this design approach was we plan to use fixed focal length camera of focal length of 80 centimeters. So it's necessary to maintain 80 centimeters from the plant surface. To achieve that, this approach was followed. Once we present this design to panel, the feedback is not satisfactory since the robot weight is too large. So they requested us to redesign the robot. From that moment, I dived in depth and focused more into the design. In this design, we plan to construct this robot using the T-slotted aluminum. This design is scalable. By adjusting the joints, we can adjust the height, width, and the ground clearance of the robot. But when I started to search for the T-slotted aluminum in Sri Lanka, it's not available. I found only 20 by 20 mm cross-section bars with a length of 600 mm. But for this project, I required 40 by 40 mm bars with a length of 900 mm. So this design also resulted in a failure. In this design, my main intention was to reduce the weight of the robot and make the bot as scalable. I thought using a telescopic tube with 4 inches, as you can see in this picture. Unfortunately, I couldn't find the proper telescopic tubes in aluminum, and also there's a reliability issue in this design as well. When the robot takes a turn, either clockwise or anti-clockwise, there's a high probability of the pressure acting on these joints. So these joints will become more fragile very soon. So this design also resulted in a failure. This design was developed based on the inspiration from a tripod. I tried to replicate the mechanism of a tripod to achieve the width and the height adjustment. But in this design, since the bottom part is too long, it disturbs the smooth motion of the robot. When we can adjust the height of the robot by basing the telescopic effect of these tubes. At the same time, we can adjust the width of the robot using this particular lever. But unfortunately, because of this part, we have to disqualify this design because that disturbs the motion of the robot and this get hit by the plant surfaces. So this design also ends up with the failure. So this is our final design which we practically implemented. We used both aluminum and steel to construct this design. The weight of the chassis without the payload is 6.5 kilograms. We can adjust the height and the width of the bot. If you consider the range of the height adjustment is 1 feet to 2 feet and the range of the width adjustment is 1 feet to 3 feet. Since the bottom part is made up of steel, the center of gravity lies down. With that, we can increase the stability of the robot. To adjust the height, we have provided the hand screws, and to adjust the width, 6 joints has to be adjusted with a 10 mm spanner. The different height to width configuration you can see in this picture. Now let's discuss about the wheel selection. There are 4 kinds of wheels widely used in the robotic applications. They are standard wheels, omni wheels, mechanism wheels, and the caster wheels. Each wheel has its own pros and cons. For this project, we have selected the standard wheels since we need to achieve 2 degrees of motion as well as the standard wheels are more suitable for the outdoor robots. Let's discuss about the embedded and electronic aspects of the project. Mainly, we can divide this part into 4 more sections as motor selection, motor driver selection, microcontroller selection, and the wireless communication module selection. So we're going to start up this section with the motor part. So motor selection is one of the important part in this project. I have to select a proper motor for this project. So to do so, I have to initially examine my robot and I have to extract the robot's specification. And I put all the specification of the robot in this chart. Based on this specification, I have to calculate the motor specification. The result says that I have required the angular velocity of 76.433 rpm and I need the torque of 16.95 kg per centimeters to achieve this robot specification. So by analyzing the available motors, I have chosen GB555 spur gear motor for this project. When you select motors, we have to be careful because there are lots of varieties of motors available. In case of DC gear motors, we have 2 types of DC gear motors. One is the planetary gear motor, another one is the spur gear motor. Planetary gear motors provides high performance but it's very expensive. But if you compare the spur gear motor, it gives a relatively good performance and it is inexpensive and it's also available in Sri Lanka. That's the reason I have chosen the spur gear motor for this project. Next, we can discuss about the motor driver selection. In general, motor drivers are used to control the speed and the direction of the motors, but we are already familiar about this motor driver. This is L2989 motor driver. The maximum current of this motor driver is 2 ampere. Apart from that, if this motor driver is the Cybertron motor driver, which can drive about 10 ampere maximum. And when I'm selecting this motor specification sheet, if we consider the stall current of this motor is 3 ampere. So I have to select a motor driver which can drive more than 3 amperes. So I have chosen BTS7960 motor driver for this project because this motor driver can handle up to 43 ampere of the current, and also we can control both the direction and speed of the robot. Next, we have to consider the microcontroller selection. Selecting a proper microcontroller is a critical task for any embedded application. We have to consider about the number of pins, hardware requirement of the design, communication protocols, architectures, programming IDE, online support, manufacturer's reliability, all these things when selecting a proper microcontroller to the project. By considering all these factors, I have chosen STM32F series microcontroller which contains ARM 32-bit Cortex M4 CPU with a clock frequency of 168 MHz. I used STM32CubeMX IDE and Kale Microvision IDE to program. We required 4 PWM pins to signal the direction, to control the direction and the speed of the motors, 2 pins with UART, 2 pins to signal the image processing unit, 1 pin to get the interrupt from the image processing unit. Then we have to discuss about the wireless communication. There are several wireless protocols are used in IoT and embedded applications such as Bluetooth, Zigbee, Z-Wave, Wi-Fi, LoRaWAN, etc. But for this project, we have chosen the Bluetooth. There are several reasons for this choice. Initially, Bluetooth has different ranges and it differs based on the class. For this project, we have chosen a class B. Since we require less than 10 meters of operating range, the operating range is reduced to 10 meters since the robot has to be controlled and navigated over the row crops. Therefore, it is mandatory to maintain the robot in a visible region of the operator.
Let's look at the design and methodology of the image processing unit. Image processing and disease prediction are done in this unit of the bot. The image processing part segment and detect the disease spots, and disease prediction unit, which is running a CNN model, predicts the type of the disease. This unit has mainly three segments: hardware selection, image processing unit, disease prediction. Let's look into the hardware selection. The part has two main hardware selection, which is camera selection and the board selection. First, look at the development board selection. Various development board and its specification were analyzed to select the correct development board for our requirement. Some of the analyzed development board are shown here. Considering the computational requirement for the image processing, Jetson Nano single board computer is selected. The board has 128 core Maxwell CUDA core, which increases the speed of prediction. The specifications of the Jetson Nano board are shown here. The current requirement for the board is 1.2 ampere at extensive CPU operation. A complicated selection in the board which changes the design structure. The camera selection depends on the board selected. The focal length of the selected camera defines the height of the board because the camera needs to be placed on a height which the plants come into its depth of field. So the camera focal length should be small to reduce the height of the board. The resolution of the camera needs to be high as details which we look on the leaf is very tiny. The details on the disease spots needed to differentiate the disease spots using the disease classification model. Based on the requirement and supported cameras for the development board, Raspberry Pi camera version 2 module is selected. Here we can see the specification of the camera. The focal length of the camera can be adjusted rotating the top of the camera lens. The focal length is set to 20 cm to get an optimum depth of field. The calculation for the depth of field shown here. The depth of field calculated for 4 pixel block. Now let's get the image processing unit. In this part, we are looking at methodology and problems encountered in this part. The process to detect the disease spots of the acquired image of the plant will be done here. Two methods were approached to remove the complex background from the acquired plant image. The green majority component based method removed a large portion of the background, but the problem was with this method is some of the plant area on the image also removed. So the next method was approached. This method uses statistical equation which was found on a research paper. It calculates super red and super green pixel for every pixel on the image. If the difference between these two higher than minus 0.05, the pixel belongs to plant and marked as 1, else it will be marked as 0. The mask of the plant which created will be multiplied by the original acquired image, gives the plant only image. The hole in the plant area on the plant only image represent the disease spots. The disease spots will be extracted from the original image with coordinates point of the holes found with the contour algorithm. The extracted disease spots will be fed into the CNN model to predict the disease. Now look into the disease prediction. In this part, we are discussing methodology and problems encountered in this part. This part of the image processing unit classifies the disease spot using the model train. The dataset was collected and created manually. The dataset has three classes which are pestatic spots, leaf miner spots, and background. First effort was extracting the feature set of the disease spots of each class. Using the feature set, various classification methods were tried. The best accuracy was achieved using the convolutional neural network, which gives around 90% accuracy. The model claim gives the label of the disease when an image fed into it. The background spots, which was falsely related by the image processing, will be eliminated here. Lots of problems were faced during the training process of the model due to small dataset. The model was overfitting when training and the accuracy was fluctuating because of the similarity between two classes. This is caused because some of the training samples were evaluated randomly.
My contribution to the project has two main units. As shown here, the first unit is the power supply, and the next one is the data visualization and the disease forecasting part. The power supply design is a very important task for a robot. The operation of the robot will depend on the power supply. The design of the power supply was approached by segmenting it into smaller parts. Initially, the primary power source has to be chosen. Therefore, the voltage and current requirements for the power supply was first found. Power has to be supplied to the gear motors, STM32 microcontroller, and Jetson Nano single board computer. The gear motor is a 12-volt gear motor which has a stall current of 3 amperes. The STM32 microcontroller requires 5 volts and the current requirement will be maximum of 500 milliamperes. The Jetson Nano board requires a voltage of 5.4 voltage and 1.2 amperes. There are 2 gear motors in the robot. Therefore, the total current requirements will be added up to a 7.7 amperes. Therefore, the primary power source must be able to provide a current of 7.7 amperes. Mainly, 3 power sources were considered: lithium polymer, lithium ion, and lead acid batteries. The lead acid battery, although it can provide high current, the weight of the battery was an issue. Therefore, it was crossed out. Lithium-ion batteries are lightweight, but they are unable to provide high current. So it was also cancelled, and the final option of lithium polymer was taken. It is light in weight when you compare it to lead-acid batteries, and it is able to offer high current. Therefore, lithium polymer battery was chosen. The gear motors require a voltage of 12 volts. The lithium polymer batteries are available in the multiples of 3.7 voltage. Therefore, the battery voltage of 14.9 was selected. Finally, the milliamp hour rating of the battery has to be chosen. For this, a research has to be done. We as a group visited the Department of Agriculture in Peradeniya. We wanted to know the standard length of a row, the count of rows in a field. This is needed because we need an idea of how long the robot has to operate in a field. The length of one row is in average 17 meters. There is a gap of 0.3 meters between 2 rows. There will be around 54 rows in total. Therefore, the total expected journey of the robot will be 17.3 multiplied by 54, which is equal to 934.2 meters. From the previous unit, the average speed of the robot was found as 0.4 meters per second. Therefore, the time taken for the robot will be 934.2 meters divided by 0.4 meters per second, which is equal to 2335.5 seconds. To know the time duration in hours, 2335.5 seconds was divided by 3600, which is equal to 0.64875 hours. So the battery required for the above calculation was found by multiplying the time found out by the current required, which adds up to 4995.375 milliamp hours. So the closest milliamp hour available in the market was 5200 milliamp hours. Therefore, it was selected. So the main power source of the battery will be of 14.9 voltage and 5200 milliamp hours. Now with the battery selection done, the power supply to the STM32 and Jetson Nano board will be supplied by using variable buck converters. The buck converter will offer the required voltage of 5 voltage and 5.4 voltage to STM32 and Jetson Nano respectively. A PCB was designed where it will be acting as a hub where the battery and the other components will be connected. Now let's move on to the data visualization and the disease forecasting. The first step was to find a proper database to save all the data. There are two main types of SQL and NoSQL. The main differences between them are that SQL has a very rigid structure, and when compared to NoSQL, it is less dynamic. For our requirement, SQL was chosen and was proceeded. The database that was chosen to work with was PHP-MyAdmin. The database was updated using ESP8266 microcontroller in the initial stage of the project. But the power needed for the microcontroller was an additional load for the power supply. The microcontroller also takes a huge current when connecting to the internet and accessing the database. Therefore, this way of approach was dropped. The alternating method was to collect the data to a local machine and then upload it to the database. This method was found to be a better solution as the data can be uploaded to the database when there is an internet connection. If not, using the microcontroller, if there was no internet connection, there would be a loss of data as the data was designed to be sent in real time. The data will be received from the image processing unit and it will be sent to the database using the graphical user interface. The method of visualizing the data was designed such that the disease percentage will be given in a grid where the grid represents the field of operation. Each blocks will denote the plant location and the diseases will be shown using color codes. If the disease is severe in a plant, it will be shown by the color red. If the plant is damaged in average, it will be shown by the color yellow. And if the plant is healthy, it will be shown in green. Therefore, when a large field is taken, the status of each plant can be grasped in a glance rather than zooming in on each plant. This method of visualization is implemented in a web application and in a graphical user interface. The disease forecasting is a part of web application where the user will need to input the temperature, wind speed, and the humidity values, and the disease percentage will be forecasted.
Okay, now finally we reached the results section. Let's begin our discussion about the results of the bot control unit. So results of bot control unit can be split as three parts as mechanical design, embedded design, and software design. So if we consider the results of the mechanical part, so as we mentioned earlier, we are among the 6 design approaches, we have implemented the 6th design. You can see this is the full width of the robot can be seen here, and can be seen the different configurations of the robot, and also you can take a look at the robot in action. Next, we have discussed about the embedded design results. So there's nothing to show you about the embedded design results apart from this circuit wiring and everything. So we have every soldering and everything has been done underneath this board, and we have connected the motor drivers with the microcontroller. So this is the results of the embedded part. Now we are going to discuss about the results of the software design results. So starting up with the control activity. So control activity, this activity is used to control the robot. The Bluetooth socket is programmed in this activity to establish a pipeline with HC06 module. Apart from that, navigation buttons. Apart from these navigation buttons, we have 2 more buttons here, which is used to send signal to the image processing unit. Then we are going to discuss about the weather activity. This activity is developed using the API from Open Weather Map. It shows the information about the sunrise, sunset, wind, pressure, and humidity. These informations are useful to the farmers to pre-plan for the spraying. Next, we are going to discuss about the heat map activity. For this project, we have interpreted the position of each plant as using the rows and columns. Since we require an expensive GPS device to collect the exact position of the plants, and since it's very expensive, we drop this approach. But the main intention of this activity is, if we develop a GPS-based data collection methodology in the future, we can interpret the disease points as heat map using the Google API. So I have integrated this activity with the Firebase and add some random data so we can see the output in this picture. So I try to mark the boundary of a farm, and I randomly generated some data of the disease spots. As you can see here, these are the informations on the database, and we plot that points in a visualized map. Next, we're going to talk about the VR activity. This activity is kept under construction because of the time constraint, but our vision is to provide the VR-based visualization to our end users to visualize the infected area of the farm. Based on that, they can spray the farm effectively.
Let's look into the results of the image processing unit. First, we look into the results of the image processing part. These are the spots which was extracted using the image processing unit. As we can see in these images, even though the disease spots were extracted, some of the background portion also came into it. The background portion will be eliminated in the disease prediction unit. Now let's look into the results of the disease prediction part. The best model achieved during the training process shown here. The loss of the model for the training and testing decreasing over epochs continuously. The accuracy is around 95%. The fluctuation in the accuracy shows some of the testing samples were predicted randomly. With this comparison, we can see convolutional neural network gives highest accuracy among other methods.
Now let's look at the results of the data visualization unit. Firstly, let's take a look at the graphical user interface. This is how the GUI looks like once it has been selected. Here you can see how the results are shown in the grid format. Next, let's look at the web application. This is our home page of the website. In this page, the user will input the date of the results he or she needs to view, and it will be redirected to the results page, which can be seen here. Finally, the disease forecasting part of the web application. In this page, the user will input the temperature, humidity, and wind speed values. Using those values, the forecast will be made. You can see some result graph that we have obtained for two diseases. Now we have reached the final part of the video presentation. This final year project is a good learning experience for us. It created a good opportunity to identify the real engineer inside us. Our depth of learning was significantly increased. In this project, we have done our best and we accomplished our target, and also our objectives were met. But this project can be further carried forward. For example, we can introduce autonomous road guiding algorithm instead of Bluetooth for navigation of the robot. We can expand to differential GPS for mapping to increase the accuracy. Apart from that, we can experiment our disease detection algorithm for various kinds of plants other than thumb puddle. Thank you.